Well, geometers, so you went to high school, and in high school you learned that there were way more ways to prove two triangles congruent than side angle side. So what we're going to do is we're going to prove that those other ways actually work. We postulate that side angle side works. We just assume that that works. But then we prove that the others work. And let's talk about how we do that. So for example, let's prove that angle side angle works. And so what do we mean by that? We mean that we have two triangles, ABC and DEF, and we set up the angle side angle criterion. Angle A is congruent to angle D, AB is congruent to DE, angle B is congruent to angle E. That's the angle side angle setup. It is our job to show that if those two triangles present that way, they are in fact congruent. And we only have one way right now to show that triangles are congruent, and that is side angle side. So here's how we're gonna do this. If AC is congruent to DF, then we're done. We'd have side angle side and side angle side. So what I'm going to argue is that's exactly what we've got. And I'm going to do that by arguing, suppose, without loss of generality, that AC is greater than DF. The argument will be exactly the same if AC is less than DF. But if AC is longer than DF, then whatever this measure is, whatever this distance is between D and F, we can come over here and find a point C prime. Then there is a C prime on AC with AC prime equal to DF. And if that's the case, triangle ABC prime is congruent to triangle DEF by side angle side. So triangle ABC prime is congruent to triangle DEF. Well, is that a problem? Sure, it's a problem, because then this angle is congruent to this angle. And that's a problem because angle ABC prime would be congruent to angle ABC. And if ABC prime is congruent to ABC, well, the only way to do that is if ray BC prime is congruent to is equal to ray BC, and that means that C prime has to be right there. And so it's a contradiction if AC is greater than DF. It's the reverse contradiction if AC is less than DF. And so if two triangles present with the angle side angle criteria, those two triangles must be congruent. And that is necessary because we're going to do something you did in high school, right? Like we're going to do something that you did in high school. Triangle ABC. If angle ABC is congruent to angle ACB, then this must be congruent to that. You're like, wait a minute, we proved that already. No, we proved that if these two sides are congruent, then those two angles are congruent. We have not proven that that logic goes the other way. And so it's not terribly difficult for us to do that. It's exactly the way we would do this with high school students, I think. We would we would drop a, well, oh gosh, I should leave that to you, shouldn't I? We should drop a, I'll let you think about that and see how you'd want to do that. Okay, I'm going to let you think about that. If I may, in an example video, I'm going to set up the angle side. I'm going to take care of this in another video. If angle side happens, angle B is congruent to angle E, angle C is congruent to angle F, AC is congruent to DF. And we play the same game. We pick a point on a segment BC such that we get a contradiction, and that's fine, and I'll set that up in the example video. You should know that angle side is a congruence theorem. You should also know that side angle is not. And you should know that side angle is not, and we set it up in the following way. So you have some triangle MTH, it's isosceles, and we extend segment HT to some point A, like so. And I should point out to you that this red triangle shares side angle with this blue triangle, because both the red and the blue have this side, and both the red and the blue have this angle. And so the red triangle has side angle, the blue triangle has side angle, but those triangles are very not congruent. In particular, angle MTA is obtuse and angle MHA is acute. And so those two triangles are very not congruent. The only time side angle works is when you're dealing with hypotenuse leg. Oh, golly. When you're dealing with hypotenuse leg, which is legit. So you have triangle ABC, but angle C is a right angle. And then you have triangle DEF, and angle F is a right angle. Now in high school, we get away with hypotenuse leg by saying, oh yes, and by the Pythagorean theorem, these sides must be congruent, but that's not a thing here. We don't have the Pythagorean theorem. And so instead what we do is we extend this ray, and then we build this triangle here. This side matches up with this one. We make this congruent to that. So this is like D prime, this is like E prime, and this is like F prime. And then we have an isosceles triangle, which means that those are congruent. And then we can use one of the other congruence theorems to make sure that hypotenuse leg is what we think it is. It is a congruence theorem. A couple of real quickies here. You're going to prove this one, so I'm going to let that go. Side is also a thing. Side is the one that to me is most intuitive and the one that nobody postulates. And in fact, the author of your book has a proof of side that uses like 5 different cases, and you should read it. You should read it because you should read mathematics and you should know how things go. I would hold off on side until after we get the hinge theorem in place. This proof is much easier after you get the hinge theorem in place. For now, it gets really weird because you have to consider a whole bunch of possible cases, and I would encourage you to read on that. But I think the proof with hinge theorem is much cleaner. Okay, so all of the triangle congruence theorems that you think are congruence theorems are actually congruence theorems, and you should know what they are.